B.
The last one, right? Yes. Right. Okay, so D, second one.
Uh, That's 4K. Wait, is it 4K? Wait, push K versus two product.
How do you know? Maybe you can write something. Well, it's always to draw and write.
Uh, um, one half. Two. We don't know V. Yeah. Wait. Oh.
Are you saying the two, like a kinetic energy, are the same?
Yeah.
How do you know the kinetic energy is the same? They
Oh.
didn't really say, right? They didn't say the kinetic energy is the same. They're saying there is something that's the same. What is momentum conservation always works as long as there's no outside force. Do you think momentum is conserved?
Yeah.
Yeah, so momentum is the same before the collision, after the collision. So what can you know then? So before it's 0 plus 0, right?
With
Momentum.
the plus 2
Yeah. Later is mv plus 2 mv, right? Let's make a difference. This v are not the same, right?
Yeah.
So should v and 1 the other v1 or v prime? Maybe v1 and v2. Better. You mean they equals to 0? Is this equal sign?
No.
Minus?
Wait, if you add them together, it's 0.
Oh, yes. Adding it. Yes. So what can you know? I can find the relation between v1 and v2, right? v1 is twice v2, right? Which means the smaller one has more velocity, right? I mean, the less mass one, right? Does it make sense? Does it make sense,
Wait.
right?
Oh. Yeah. Wait. Yeah, because the mass is.
This should be plus, and this should be negative. So v1 equals to 2 negative v2. Does that make sense?
Yeah. Yeah. So
So I might as well want to like draw it so they go into direction. So if I draw it, it should be, this is V1 and the girl is V2. No, this is V2. I can write this 2V, 2V2. Negative 2V2. Does that make sense?
Mm-hmm.
And this is this is mass, this is 2 mass, 2m. And well, before it, for the momentum conservation, we normally draw two graphs. One is before, the other one is after. Does that make sense? We actually normally always draw it. For some of the tests and then the answer sheet, they actually draw it even in the answer sheet. Does that make sense? The conservation momentum, we always show what's before and what's after. You know, with all the, you know, mass and 2m and 0, 0 velocity.
Mm-hmm.
Okay, now we know v1 equals to 2v2, and then?
So that means it's over 4. D.
So how, which one you want to choose then?
D.
You approximate, right? We can deduce all the way. If we can deduce all the way, we shouldn't use approximation. Even if we use approximation, we should try to use patterns and formula probably. So K is what? 1 over 2 mv1 square, right? Does that make sense?
Yeah.
Which is 1 over 2, 2v2, negative 2v2 square, right?
Yeah.
And let's say K brother is K2, which is 1 over 2, 2m, right? Times v2 square, right?
Mm-hmm.
This is mv2 square, and this is a 2m v2 square. Does that mean?
Mm-hmm.
So which one you want to choose?
Oh, wait. Oh. It, so,
You want to choose C, right?
wait, no, D.
Wait.
Wait.
This is the girl. I should write it here. Girl.
Oh.
This is the brother.
Well, the girl has twice. Oh. Yeah.
So this one is K. So on the other hand, this one is K over 2, right?
Yeah. So it's 2. Okay. Yeah.
So what should we be careful about this? We should always deduce, right? Write everything. If you only put it in brain, well, that's why the physics scientists sometimes turn to math scientists for help. Because the process is more like a mathematical process. So yeah, we should, well, use math more and more. Is that okay? The second one? But this one also people make mistakes, which you see. One is conservation momentum. The other one is well, definition. But you have to deduce all of it. Don't you have to write deduce all of it. It's a 3.
Constant. At time. Oh, you just big 5. Right?
Yeah. Big 5 question.
So just
Oh, I also want to mention something. Sorry, gotta mention something about question 2. Is let me see, where are the keywords? Whenever you see, well, there's no collision. Too bad. I said collision must be always, generally, almost say 90% is momentum conservation. This one is, they don't have that, so that's why picture is more important. I mean, if you write it like this, if you write it like this, you probably feel that way, right? Before and after. So that's why, let's say the keyword is important. Also, the graphing is more important. So 3.
Okay, so you just plug in these two. So then,
Yeah, you can have a range then, right?
yeah.
One like the minimum, the other one maximum. Substitute.
Uh,
Which formula you want to use?
Oh, x equals v0 t plus 1 half vt squared. So time is 1, so then 1 times 1. So x equals 3 plus 1 half 3 times 4. Wait. Oh, it's the other way, so it's negative acceleration.
Yeah.
Yeah, but that doesn't make sense. That's not the answer. Wait. Oh, because it's delta. Oh, yeah. Okay, makes sense.
Yeah.
Okay. Let me do it again then. X equals 3 plus. Wait, no, it's minus 1 half. 1 half 3. So then that's 3 minus 1.5. So that's 11.5. See?
Yeah, that seems right, but you have to be careful. One thing is this one tell you x equals to 10. Do you think that's gonna help?
Yeah, because then you can find the delta x, right?
Yeah, so that'll be delta x related. What you find is delta x. And what he wants to find is the position of the card, which is x. So the difference, this is the very first time we did this, I think. Although they write it in the Big Five. I never really like it, but it's really helpful in this kind of situation. Delta x is 80%, and this is the other 20%. They want an x. So you should substitute 10 in here. And also, if that's positive 10, then you have to write this one negative 3 times 1. So all positive negative is extremely important in Big Five because it's a vector equation. Because Newton's is vector equation, which is better than the great scientist Descartes. His one is doesn't really involve with vectors, so positive negative not that important. So that's why he used his formula can be only used in some of the occasions. So that's why it's 1/2. This one is positive 3. Positive what's the 3, right? So this is positive, right? This is negative, right? And 1 squared. Does that make sense? Because if you use yours 1 times 2 plus 1/2 negative 3, it's actually okay when it's a delta x. The magnitude is okay, but now like positive negative is extremely important, right? Let's say it's always important. That means be careful with positive negative. So what's this? I think it's 8.5. Right? 10 minus Is it 8.5?
Let me check.
10 minus 3 is 7. 7 plus 1 over 2. Yeah, it's 8.5, right?
Okay, yeah.
So which could be probably it's B, right?
Mhm.
Does it make sense? Same way we do 10, right? We just substitute 6 in here, right? Everything else is the
Yeah.
same. So what should we be careful about question 3?
The delta x.
Yeah. So we should make the difference between delta x.
But can't you take the delta x and add it to x initial, or you can't do that?
You can, if you want to use delta x formula, it'll be this one. But then delta x still equals to x minus x0. So your x is going to be x0 plus delta x anyway.
Okay, but before I got the delta x was like 1.5. Wait, let me do it again. Let me see. 10 times 10t.
It's negative 1.5.
Oh,
It's because you put the sign in a different direction.
oh, okay, that makes sense. Okay.
Because if you name this one x equals to 10, for example, if this is 0, this is a 10, right? This is a positive 10, then which means he's in negative x direction is going to be this way. So the velocity is negative 3, right?
Hmm.
And acceleration is positive 3 in that direction, right? In positive x direction. Does that make sense? So 3 is okay. The positive and negative is kind of important, right? And also make the difference between these two kinds of same big five formula, right? One is delta x, the other one is x equals to x0 plus that delta x, right? That one is electricity. We don't have to take 5. So 5.
Point H. Potential energy. Okay. In which segment does a net force exerted on the object have the greatest magnitude? It would be I, right? IJ. Right?
You're gonna choose IJ.
Yeah.
It's because it's steep, right?
Yeah. And then it's this is the potential energy, so it's a lower means more kinetic.
So I guess the delta E, which is the work, equals to F times D, right? So delta E equals to your U, right? So which means F equals to U over D. And so the greatest slope, right? If it is greatest slope, this slope and this slope, which one is higher?
It would be LM. Oh, because you can have negative force too.
Yeah, because if you want to say magnitude, then it's D, right? Slope LM is the highest. Right?
Okay, makes sense. Yeah. Okay, yeah.
So
Which connects the object at point K. Well, no energy enters or leaves, and then here it's 5, so in total there's 9. So this is, wait, that's the, Mechanical energy is 5. Wait, kinetic energy? Point K. Huh. Wait, at point H. Mechanical. Oh, wait. Wait. Total. Okay. So then it's 3?
3, which is C, right?
Yeah.
I guess this at K, potential energy is 2, right?
Yeah.
This is 2. Must have another 3 there, right? Because the total is 5, right? Because the mechanical energy is conserved, right?
Yeah.
Okay, yeah. 7.
Which of the following describes the magnitude of the momentum object? Magnitude of the momentum of the object. First 2 straight line segments. HI and IJ. Momentum. That's velocity. It's still moving. And it's C, right?
Yeah. HI is constant, but not non-zero. Yes. And IJ is IJ is increasing. Why IJ is increasing?
Because it's going, it's accelerating. There's like less potential energy,
Yeah.
and momentum is mv, and v is increasing, so momentum has to too.
Yeah, because your potential in IJ potential energy is decreasing, right?
Yeah.
From 4 to 2. So which means on the other hand, the other energy must be increasing, which is the kinetic energy must be increasing. If you increase, then your V increase, then your momentum increase, right?
Mhm.
Let's see, 9. Wait, not 10. 12.
Toy doll and toy robot are standing on a frictionless surface facing. Oh, this is like before. Doll and robot. 0.2. 0.3. Pushes the doll to force 0.3. Newton of the robot. Okay. I don't know if it's okay. So you can do the conservation momentum, right?
Yeah, yeah.
Wait, over the wait.
Momentum is conserved, but I don't think we
Oh, you don't need
need to
it.
use. We don't really need to use it.
You do the energy. Wait, if he put in force of 0.3 newtons this way, that means there's another force 0.3.
Yeah, Newton's third law is another
Oh,
0.3.
So then 0.3 times the 0. Wait, time.
But you find acceleration, you need to divide it by the mass of the robot himself, right?
Oh, Oh, we want acceleration.
Yeah.
0.3 equals 0.3. Okay, so C.
Yeah.
Mhm.
So yes, you want to use momentum. Yes, use momentum also can find it. But this one, because momentum and sigma F equals ma is the same thing as Ft. Like I mean dot at P or dot MV, right? They actually is an equivalent equation. Pretty much the same. One can be deduced by the other.
Mhm.
So if you really want to use that one, you can actually. You just find the V, right? Wait, you find the V, you also have to find the time. So yeah. Wait, for this one you have to use sigma F equals ma, right? Don't use momentum. You can, but there's not enough information, right? For 12. Because I don't know the velocity afterwards. I don't really know the time, right? So don't use momentum for 12. Not enough information for that. Let's say 13.
These are right. Horizontal surface. Short-time abs. Collides elastically. Um, if it's elastic, isn't the block zero, not moving? If the block collide
With the sphere?
if the block is if it's elastic collision, doesn't that mean the block afterwards is zero?
What is zero?
The speed of the block and
Even afterwards?
yeah,
What do we know about elastic collision?
and that all of the energies
The energy is not lost, right?
yeah.
So it didn't really say, which energy is zero or not. No, which velocity is zero. It only say you don't lose energy. So what's the energy before is what's the energy after.
Okay. So we can do momentum, right?
So we
Wait.
still have to deduce all the way. This is unless you remember the other hidden formula. So this is V0, and later it's becoming actually we don't really know. Let's have a velocity there, and they probably have a velocity this one, right?
Inter prime plus 2 V prime, right? For the momentum.
Yeah.
And then
And then you can also use the elastic collision. Another equation.
Okay. 1/2 V0 squared.
Yep.
Equals 1/2 mv0 prime squared plus 1/2 mv prime squared. All the 1/2s cancel out. And the m's cancel out too, right?
Sure.
Wait, and then that means v initial v0 squared equals v0 prime squared
I mean, prime. Or the-
plus v squared v prime squared. So now we can wait, let me see. It's 2m. Oh wait, there's still an m here.
yeah.
mv squared prime. Wait, mv prime squared plus v0 prime squared equals v0 prime. Then v0 equals mv prime plus 2mv prime. Well, then you have v0. That doesn't really help. Oh. Hmm.
We can just solve this. You remember we solved this kind in a like a free response before.
Yeah, wait.
Yeah, let me just do it because there is, remember, there is in this one and this one, there is a difference of square. So v0 squared minus v0 prime squared equals to, this is v, right? This is v.
Yeah.
Yeah.
V prime.
Yeah, v squared. And
V
and
squared.
this
Yeah.
is mv. Then v squared. Yeah, and so this v0 plus v0 prime and v0 minus v0 prime. So this one can be v0 minus v0 prime is 2v, right? This one is 2v equals to v0 minus v0 prime equals to v squared, right? Does that make sense?
Mm-hmm.
So now I can simplify v in here and v in here. And so I know v0 minus v0 prime, wait, that is the, let me think, which one is it? Oh, this one is too big. This one plus. Plus that would be v over 2, right?
Mm-hmm. Wait. How did you get the 2v over here?
Oh, 2v is here because I moved this v0. I mean, I moved
I
this
see
one in
now.
here.
Okay. Yeah, I see. Okay.
2v.
Yeah.
So I'm using the 2v in there, right?
Mm-hmm.
And so that's why I can say you want to find out the speed of the block. Let's find the v0 prime. Now I have this one and this one all together. v0 minus v0 prime equals to 2v, right? I want a v0 prime, right? v0 prime, I minus that, so 2v0 prime equals to, I minus that equals to 3 over 2, actually negative 3 over 2v, right? That makes sense? So v0 prime then is negative 1 over 2v.
Mm-hmm.
Make sense?
Okay. So negative 1 over 3v. Okay.
Yeah, so now I can just use all the v in there. v0 minus v0 prime, negative 1 over 3v plus 2v, right?
Mm-hmm.
And then V0 is 5. V, 2V, 2V, this is positive, and then this 5 over 3V, right? Equals to V0. So V equals to 3 over 5 V0. That make sense?
Mm-hmm.
And then what's my V0 prime is negative 1 over 3 times that. Wait. 1 over 3. Mm-hmm. Oh, since this is a choosing question, I don't want to deduce all the way. This is a lot of time use. There's another way to do this if it's a choosing question.
Can't it just be A? Isn't
Hmm?
it just? Is not just A?
Yeah.
Because the V prime, V0 prime is negative 1/3, so that's it, right?
Yeah. Wait. V. It should be A. Let me check. It should be A. There's another way of doing this. I deduce so much because I want to know the process, but process is the same anyway. Does that make sense?
Yeah.
Use the difference of square for the second equation, and then find the system equation. But this one has another way to do this. I can just check out ABCD. Does that make sense? There's a lot of letters in there. So many variables. I can just check whether they are like somehow conserved or not. I can check ABC. Does that make sense?
Mm-hmm.
So this one is definitely wrong. B is definitely wrong.
Yeah.
C is also definitely wrong, right?
Mhm.
So the only thing that's left is A and D, right?
Mhm.
Because BC's momentum is not even checked, right? It's not even conserved. Does that make sense?
Mm-hmm.
So I have to check AD, and then I can just substitute. Does that make sense? D is not working. It's because if I do that 1 over 2 mv0 square plus the other one is 0. Okay, sure. The other one is 0, right? Compare with what's before. Let's see, what's before? What before is also 1 over 2 mv. Oh, this one checks for the conservation of energy, but doesn't check with the momentum. Because before is mv0, right?
Mm-hmm.
And now is negative 1 mv0. So which is totally not conserved, right? Does that make sense? So I can choose A. Is it making sense?
Mm-hmm.
I can also check the same thing with BC. Let me check it. So that'll be because still before is mv0. This one is negative mv04, right? And plus that 2v0 over 3 times 2m. This is positive. If I add this 4m v0 over 3, if it is less, this one is checking actually. Right?
Mm-hmm.
Okay. mv0 plus 2. Oh, this is to the right, so it's not working. Plus, then you are 4. I thought it's positive there. Then that's a 4. That's a 5, right? So it's totally not checked with the conservation of momentum, right? So that's why B is out. Does that make sense? Because
Yeah.
momentum doesn't involve with squares, so we check momentum first, and then we check with the energy, right? And C is after is 0 plus momentum, and then 2m time v0, right?
Mhm.
Which is also not conserved anymore, right? So before is m0, right? Why is it so big now, right? So that's why BCD is out, and A is the only one that checks. Does that make sense? Don't use what I just deduced. If it is a free response, do that way. But unless you can't really, eliminate the wrong answers, then use that way. Is that okay?
Mhm.
Yeah, let me explain that why that I use, for example, let me deduce all the way. M1, V1, M2, V2 equals to the M1, V1 prime plus M2, V2 prime. This is a collision between any two. And the other one is 1 over 2m v1 squared plus, I'm talking about at the same time elastic collision, and v2 squared plus m1 v 1 v1 prime squared and m2 v2 prime squared. So I still use difference between squares. So make this one and make this one in here. Make this one in here. So it's 1 over 2 m1 times v1 squared minus v2 squared. Does that make sense? And this one is 1 over 2m v2 prime squared minus v2 squared, right? Does that make sense? And in the same way, I can make it in here and make it in here. So I have v m1 v1 minus m1 v1 prime and equals to m2 v2 prime minus v2. So you can see that m1 over m is 1 over m is 0 out. So m1, this is v1 minus v2. Does that make sense? So I can find it in here, right? See?
Yeah.
So if I find it, this is v1 prime actually. v1 prime, v1 square root, yes, v1 and v1 prime. And this one is m times v2 prime minus v2 plus v2 prime plus v2. And because of this is here, so I can simplify this one and this one. This is v2, m2. Simplify. Does that make sense? v1 this is v1 prime, v1 prime, right? And then that v2 prime minus v2, sure. And then eventually is v1 plus v1 prime equals to v2 plus v2 prime. Does that make sense? So always use the difference of squares. Does that make sense?
Yeah.
So eventually what we find is actually v minus v2 equals to v2 prime minus v1 prime, which means the relative change for the speed is actually the same. Does that make sense?
Mhm.
That's what's happening when it's elastic collision, and also of course momentum conserved, which is almost always in our situation. Is that okay? 13?
Mhm.
I'm just saying, if it is free response, big deducing problem, always using square. Yeah, different squares. 14.
One whole mass m so is almost what is the ratio kf to ki? Oh, this was not bad. What if these? Do you need conservation of momentum?
Yeah, collision. Yeah.
Uh, V equals. Well, this is the inelastic collision, so you can. It's the shared velocity, right?
Yeah.
So it's 4m times v. Wait, v prime.
Sure.
What is the ratio kf to k initial? 1/2 mv squared equals. Oh wait, this one that energy isn't conserved, right? Because it's elastic.
Yeah, inelastic, which is sticking together thing, is always inelastic.
Yeah. Wait,
Perfect.
with mv squared. And then kf. You want to find the ratio kf over kf to ki. That's ki. Wait. Okay. Kf equals to 1/2 4 v prime squared.
Sure.
K initial equals 1/2 v squared. Can we get the
Sure.
v? So then,
But this one you can deduce something. This equation, you can deduce the v and v prime relationship.
oh wait, yeah, v equal 4 v prime.
Yeah.
And then we can. So then this is 4. Wait, no. This is 4 v prime. So then that means this is 4 v prime squared.
Yeah.
So this is wait, let me erase. So that means this is 16 v prime squared.
Yeah. Wait, there's a 1/2. You mean 16, which means 8, right?
Yeah. Okay. Yeah. So 8m v prime squared.
Yeah.
This one 4. Wait, no, it's 2v prime squared.
Yeah.
That's the final order initial 1/4, so it's d.
Yep. So this
Okay.
reminds me something about one of the worst time in high school physics is we do not deduce. That time I almost lose confidence and lose almost all hope in physics. But when you start to deduce, that'll be okay, right?
Mm-hmm.
Yeah. I don't think we were born with like a mathematical brain. We were born with, so we have to practice that deducing and medical deducing, right? Mathematical deducing. But this is good. 14 is good. It looks like that way, right? Let's do 15.
A meteoroid is in the circular orbit 600 kilometers above the surface of a distant planet. The planet has the same mass as Earth, but orbits 90% of Earth. The acceleration from the meteoroid to the gravity is most nearly exerted by the planet of the meteoroid due to gravity. 90% of Earth. Same mass, but different radius. You need the universal gravitation, right? G. Acceleration of the meteor. Is it A? Wait, no, wait.
You had to deduce all the way. That's why I mentioned 14. Just
Okay.
deduce all the way. When do we not deduce? When it's really impossible. So we deduce, we draw the diagram, understand the phenomenon, observe, and deduce all. Yes, use that deduce.
Over D squared. D 600. 600 squared. This is 0.9 times the mass. 0.967. 5, 7, 3, 3, and then 600, and then 5, 7, 3, 3.
Yeah.
Okay. Okay. So then 600 plus the radius.
Yeah.
5, 7, 3, 3.
That's 0.9 times 16,
yeah.
right?
6, 3, 3, 3.
Yep.
That's the distance.
Yes. That's
you don't really need the mass of the meteor, right?
Yeah. Because when you find the acceleration, you're using that divided by the m2, right?
Yeah. So this is just all over. Oh, so you have to find the mass of the Earth, right?
Yeah.
Oh. So, 10 equals, what's the universal gravity? Equals 6.67 times 10 to the negative 11 times 6370.
So this time is gonna be 10. Why do I don't need to find it? It's because, and also because I don't really know math of the Earth, right? They don't provide this, right? Oh wait, we don't know. We know. So which means at this point, you can see when you divide it by m2, by this fg, which is acceleration, right? And then what's left is gm1, which Earth of the Earth mass, divided by this. Although it's 6333, but you can say 6333, isn't that almost as 6370, right?
Mm-hmm.
So it's almost like Earth, right? It's almost like the radius of Earth, right? The thing is, if the radius of Earth, this one we know is g acceleration, right? Mass there time r squared of the Earth, right? So this is around 10, so this is also around 10. Does that make sense?
Mm-hmm.
So we should choose between C and D, right? Which one you want to choose?
Oh.
Magnitude is C and D.
C? Where?
It's C, right?
Yeah.
So this is just the direction of the velocity of this, right? But you're actually in here. This is the velocity. That's the velocity of that. Right? I want to acceleration. Acceleration is circular acceleration, right?
Mm-hmm.
It's by the centripetal force, right? Is it making sense if I choose C?
Yeah.
And also because math of the Earth we don't really know, so we kind of have to force ourselves to know that G equals to gm over r squared, all about the Earth, right? Which is around 10. 16. So 15 is a little new though.
Torque on the meteoroid with respect to the center of mass of the planet. Why or why not? Torque on the meteoroid with respect to the center of mass of the planet. Uh, does it have, uh, mm, does it have a, it has to have a torque on the meteoroid, right?
Well, we have to draw the diagram. How do you know? This is the velocity of that.
Yeah.
And this is the gravitational pull, right?
Mhm.
So if the force, the only force you give is this, right? Which means we are talking about, is this force making a torque? So this, right? Does that make sense?
Mhm.
And your center is in here, right? Remember, FR perpendicular is, this one is what? The distance from the pivot or axis to the action line of the force, which means this action line of the force actually go through that, which is make that R0, right? Does that make sense?
Mhm.
We
Right.
choose between C and D, right?
Oh,
C is definitely wrong. Force is not
so,
negligible. So this is another way of saying that R perpendicular is 0, right?
oh,
Again, because
okay,
you exert a
okay,
force go through the center or the
okay.
pivot, right? Pivot or axis, right?
Mhm.
Does that make sense?
Yeah.
So I think you should remember this. Sometimes you also say FL perpendicular or FR like sine theta something. This is more like essential. This is deduced all the way. Sometimes it's a little confusing. This one is preferred. And just use trigonometry. Is this okay? So you have to draw it. You basically, for this kind of whether there is a torque thing, is you have to find the pivot, right? Or the axis. This is the axis, right? And this is the force, right?
Mhm.
For example, if you have a force in this, for example, if this is a rocket, you know, you have a little fire engine there, and that make the torque in this, right? See, for this, right? So you make that. So the R perpendicular is this, right? So this is let's say this is fire of the engine of the rocket, F time R perpendicular, right? That would be the torque, right?
Mhm.
So that force, but not the force for gravity, right?
Mhm.
The 17.
This satellite that particular orbit around Earth is usually not rotating. Hmm. How does it affect the mechanical energy of the satellite Earth system? Um, it's adding mechanical energy, right? But, huh. This force goes this way. This force goes this way. That's spinning it. Um, hmm. I should have the orbit. Hmm. Wait, this wouldn't increase the energy in the satellite Earth system, right? Because it's just adding energy to the satellite, not into the system, right? So then it would be A. Oh, not rotating with the center of S. Oh, then it should be. Turn up. Turn it normal and then turn off. So then, not rotating with the center of S. So it's here. It's gonna be like all wobbly. And after it turns off, and then stay that way. So that would change the shape of the orbit, right? Because then you have the center like changing, and then so it's D. I can't hear you if you're speaking. Wait. If you're speaking, I can't hear you. Shape of orbit. Uh, I can't hear. I can't hear you.
Can you hear me now?
Yeah.
I get the same. That's a second.
Is it okay?
Yeah.
So it's gonna be choosing C, right? Is it making sense?
No effect on the because it's rotating around the.
Yeah, it's still rotating around the Earth, right?
Yeah. Oh, okay. Yeah, that makes sense.
So the shape is gonna be only influenced if it be changing, then it's influencing the force. The force should be the same.
Mhm.
So if this is the Earth, you're giving a force in here, that force balance, right?
Mhm.
You only rotate, but you don't really influence things. But you can rotate yourself. But generally, when you do that, it doesn't really change. You know what I mean?
Yeah. Okay.
Okay, let's do 18. Oh, not 18. 19.
Spreading unstretched without zeros. Lower, lower. What's a maximum height? When released, wait, after release, what height will the kinetic energy of the block be maximum? Oh, isn't it just L0? Because then that means all the force in the spring is being put in the block.
Why?
Wait, it shouldn't be L0 because if you press it down and then it goes, the spring will go back to L0 because it's wait, is it attached? Oh, it's attached. So then it would be LEQ, right? Because that's the equilibrium point, right? And then the spring releases and it just goes to that point, and then the block would be moving the most.
So conservation of energy, right? If they say maximum of kinetic energy,
Mm-hmm.
there should be minimum potential energy, right?
Yeah,
When is the minimum potential energy?
when the spring is stretched out, like the most.
But isn't that one higher potential energy? L0 compared with L.
Wait, yeah, so that's L0 then, right?
Let's start from the beginning of this process. When you L0, a block is attached to the top of the spring and is slowly lowered until it is at rest. Slowly, which means all kinetic energy is kind of zero, right?
Mhm.
So initially, all the energy is elastic, right?
Yeah.
So isn't this time is the minimum potential energy?
Yeah.
If it is minimum potential energy, and the energy is conserved, the minimum potential energy, which means also the largest kinetic energy. Does that make sense?
Okay, yeah, that's what I was thinking. Yeah. Okay.
So I have to choose B, right?
Yeah. Okay.
Then they said the blocks then push down until the spring is compressed to the outlet. Oh, even if you push, the energy is still conserved.
Uh-huh.
So at this time, it's balanced with this. So can I choose B for 19?
Yeah.
Let's say 20.
Who frictionless lab cards are from wait. No. Students measure the magnitude and duration of the force on each card. Illustrate in parts and completed data table above. Wait. Final two. Uh, okay. Okay. Wait, this is easy then. You just do 1 half mv squared. 1 half. 1. Wait. 10 divided by 2, 5. Wait. So this one's 25, right?
Yeah.
So it's part 1.
Yeah. Right.
Okay.
Yeah.
That's straightforward. Let's see.
21.
Simple pendulum consists of a sphere tied to the end of a string of negligible. A simple pendulum consists
Is there
of
a,
sphere.
let me see, is there a graph? No. I'm gonna draw it out.
And wait, a sphere tied to the end of a string of negligible. Sphere is pulled back until the string is horizontal and then released from its two ends. What angle will the string make with the horizontal when the kinetic energy and the potential? Let's start here. And then this is 0. This is 100. Isn't it just when it's 45 degrees?
Hmm.
Or,
What angle will the string make with the horizontal when the kinetic energy, and potential energy, here Earth system are equal?
uh,
Potential energy before is mgh, right?
yeah.
mgl for this one.
MGH. And then the other one is MV. So
If they're equal, which means this must be 0.5, right? MgL. That means the kinetic energy, right? And potential energy at the same time, right? So this happens as like a 0.5 above the lowest point, right?
yeah.
So which this is the height. And this is L/2, and this is also L/2, right? This happens that, right? So if this is L/2, so this is L, now that'll be sine theta. With the horizontal angle, the string with the horizontal is this one. So this is also the alpha they want to ask. So sine alpha is 1/2. So alpha is 30 degree, right? Is it?
Wait. Oh. Okay, yeah, makes sense. So then it's less than 45 degrees. Okay, that's wait, if it's less than 40, okay, that makes sense.
It should be C, right?
Yeah.
If they're really equal to each other, it should be half. If it is half, well, before this is MgL, and now half of that. So this must be L/2. Yeah. But you should see, right? Okay, 22.
A stationary car attached to a force gauge is on the street. How does the momentum of the car change anytime it moves 0 to 20 seconds? This is force and this is time. Force over time. Force over time, that's the momentum, right?
You mean force over time?
Yeah. Right? Force times.
I think what you mean is Ft is momentum.
Oh, so then this is the
P, right?
so then the area under this is the momentum, right?
Yeah.
So it's like this. Wait, how does that momentum increases in magnitude? Momentum decreases in magnitude. Reverses in direction. Wait, what's the area to here? Then this is like here.
There's someone is pushing this, right?
Yeah.
Of course, the velocity is changing, right? Constantly increasing. Momentum increase, right?
Mm-hmm.
And then suddenly you're not going for this push, you go for this push, right? That's why it's negative, right?
Yeah. So
When
then,
it's around here.
so then it changes direction, right?
Which means after that, for example, saying this is saying 100 meter per second, and I mean at that time, if you change the direction, and then mass time that, then it started to decrease, right?
Yeah.
We would reverse now CD okay. But once we reverse direction, I don't think it's reverse direction. Oh, I would have a calculator actually. Right, this is 4 time what? 4 times what?
Mhm.
Is it 15?
Oh.
I think it's 15, right? 4 times 15, which is 20, right? So your momentum
Yeah.
increased by 20. And now your momentum decreased by saying negative 8 times 5, 15 to 5, right?
That's 5. So, oh, so
Negative
that's
40. So you can reverse direction, right? Maybe
Yeah.
after a little while, right?
yeah. So then it's D.
Yeah, D, right?
Mm.
You should remember this one, right?
Yeah.
And also, we can do the phenomenon with, increasing the velocity and decreasing velocity. Right? How about the 23?
$23. During which of the following times the car turns to position at T0 meters per second? Which of the following moves the car return to its position at time 0? Oh, this is the. You can do the area, right?
Yeah.
Mm.
Is there, yeah.
So that's like 1 times 1 over like 3, right? So that's still like 1. So it went like this interval, it went 3 meters. So then, wait, no, wait, yeah. So once I get to 3 here, it's like no, it's like here, right? It's like about here, right?
Yeah, I think it's around there. So it's a balance, right? Positive displacement, negative displacement balance, so you return to the original position.
I think it's B, right?
5 to 7. Let me see. 5 to 7. So let me mark it carefully.
1, 2, 3.
If that's your case, that's 5 to 7, right?
Yeah, it's not.
I think it's a little too small, right? Compared with this one.
Yeah, it says can't be 3 to 5.
7 to 10, right? Is more likely.
Yeah.
7 to 10 is probably more like it.
Yeah. 10 to 12. Yeah.
Also, this one is higher than 1, so yeah, you might use 7 to 10, right?
Yeah.
So with this kind of thing, you have to draw the diagram carefully, right? Also compare, right?
Mm-hmm.
26.
An emission point right consists of a large vertical wheel of radius r that rotates counterclockwise on horizontal axes. Points A and D represent the position of a person. Which of the following best describes a vector's linear and angular velocity all path? Angular velocity is constant, and then the linear one is changing, right? That's how like circular motion works.
So which one you choose then?
D.
Linear change direction. And angular do not change. Sure, why not?
27.
Passing through point D, normal force. Normal force is same, right? Oh, actually, wait.
Probably not, right?
Wait, but the
See, because the velocity doesn't change, right? The speed doesn't change. So what's happening here, we find the diagram at A is, this is 0.8. That's a FG, that's a FG, right? Both of them are taken as 1.8 FG equals to mv squared over r, right? Wait, oh, I was wrong actually. This is at A, right? Wait.
Yeah.
I think. Highest and respective weight sits upright. 0.8, 0.5. Oh, that 0.5 is given to which direction? Oh, that's my case. If you're sitting there, upward. You know, there's a chair, right?
Mm-hmm.
So what's give you is this direction, right?
Yeah.
So it should be 0.2f, right? Not 1.8. 0.2f here, right?
Yeah. Wait. Wait, so like where's the 0? Oh, I see now.
This is A. And now we are adding D, right?
Mhm.
What's happening at D?
D is the lowest.
So the centripetal force at that time, we should also provide it, right? Which is all the sigma f, right? And which this mg is already in this direction, but the force for the centripetal force in here, so the normal force must be in here, which is also coming from the chair. But this chair must provide a little bit more, right?
Because it has everything else under it, right?
Yeah. So Fn prime. So Fn prime minus Fg, right? Because this is mv squared over r. This is also mv squared over r, right? Because it's the same velocity, right?
Mhm.
So which means this one minus this one is that 0.2 FG anyway, right? Is that what it is?
Mhm.
Because centripetal acceleration is the same, right? V squared over R is the same. So this MA and this MA is the same. So eventually it's Fn prime minus mFg equals to 0.2 Fg, right? Which is the centripetal force before, right?
Mhm.
Which is 1.2 Fg, right?
Mhm.
Is 27 making sense?
Yeah.
You gotta think about the velocity, the speed doesn't change, right? So do basically is Fc equals to, well, sigma F C in A, right? And also MV over R. And this at D also do that, right? FC also equals sigma F equals to MV squared over R. And you have different F sigma FC and different sigma FC at A and D, right?
Mhm.
Does that make sense?
Mhm.
Oh, I kind of have to get up from class. So you can do 28. Try to do it yourself. I'm gonna send this in the group though.
Okay.
Of course, skip the wave, skip the electricity, skip the math, and
Okay.
right.
Yeah. Okay.
Okay. That's it. Have a good day. Let's see.